Hello, welcome back. Today, we want to talk about compound interest. So, compound interest is a way to often used by banks and other financial institutions to basically generate money over time. So, for example, if you have a CD in a bank or something like that, then your account generates interest over a certain amount of time. Or interest is also used, for example, in if you buy a house or a car, then there's also a certain interest that goes with that. We have to pay on top, as part of the loan, which you pay on top of the actual price of the house or the car. And so, in part, that's how money is made. So, for example, if you put a CD in a bank or money in a bank, you're lending the bank your money, and so the bank uses that money to make loans. And then for that, you get a certain interest rate, which is usually, unfortunately, kind of small in most cases with banks. And then if you finance a car or a house, that interest you pay is then for the interest company, the banks or some or other institution like that. Basically, that's how they make their money off of that loan, is by charging interest. So, I want to get a basic idea of how some of this interest is calculated, and we're looking at what's called compound interest, where basically interest is the amount is increased over some certain amount of time. Okay, and this is actually an exponential type of growth. So there's something called simple interest, which I'm not sure how much it's actually used, which is just a fixed amount of interest added every certain time period. And that interest will never, the amount that's added to it will never change. But with compound interest, if you put in $1,000 in a bank, and after let's say after a year, you now have $1,100 in the bank, then the interest rate you make for the next year then is based on not only what you put in, which is $1,000 to begin with, but then also the extra $100 you gain. So actually, it grows upon itself, and so that actually becomes an exponential type of growth instead of just a linear type of growth or a constant growth. So our goals for this will be able to calculate what are called future values. We'll explain what that means based on compound interest, and also want to be able to use logarithms to determine the time needed to reach a certain future value. Those are both important questions to answer. Let's look at now the compound interest formula, and this is called a periodic, basically based on some compounding period. So this is the formula. Let's explain what everything is and where you start. So P is what's called the principal, sometimes called the present value or initial value. This is what you initially put into the bank or put into this loan or put in this institution. Let's say you have a bank CD. This is the amount you're initially putting in. Okay. Now, you're given that some interest rate, R, usually given as a percent and usually an annual interest rate, but in a formula, you always put as a decimal that goes right here where the R is. Now, then that sum is have some number of what are called compounding periods each year where the interest is calculated. And here below, it gives some common interest periods. Basically, that's part of the formula. So the n goes right here and also right here in the exponent as well. And here are the common compounding periods. So annual interest is once a year. Sometimes called semi-annually is twice a year. Actually, I apologize. I realize this is, I should change this. So I used M down here. So let me change this. Most other textbooks I've seen is N. Here they're calling it M, so to be consistent. So M is our compounding period per year. Let me change it here as well. So annually is once a year. So M is 1. Semi-annually is twice a year. Quarterly, 4 times a year, is as you expect, 4 times a year. Monthly is 12 times a year. Weekly is, another typo. That should be 52, not 42. 52 every week or 52 times a year for 52 weeks in the year. And then daily is 365, and we'll just set of technically a year is 365.4, but we'll just use 365. And you can also potentially calculate interest based on what's called even, I guess, hourly and every minute, but that's less common to think about. That's even more complicated. And so when you put all that together, and also the time, T in years, is how long the amount stays in the bank. Now, also time here is always in years. And for what we're using here, it's always the same as the amount of time your interest rate. Now, then once you put all that together, then the A is what's called the future value at the end of T years. So you put the principal in for a certain interest rate, usually stated as a percentage and placed here as a decimal. The number of compounding periods you have per year is M, and then T years. And that will give you the final amount, A, or what's called the future value at the end of those T years. Now, there's another form of compound interest, which is actually called continuous. So as I said, if you imagine, say, just compounding daily, instead of calculating the interest daily, calculate every hour, every moment, every second. You keep going is basically continuous compounding, calculating the interest, and that's called, or that is what's called continuous compounding. And that's given by this formula here. And actually, you can show that if in the thing about what's called the limit, or if you make m as large as possible, it looks more and more like this. So here, the variables we have are the same. This is base E. So you have P, still the principal, your initial amount. Then R is interest raised a decimal, then T is your time in years. So that's called continuous compounding. And continuous compounding is actually the fastest, or generates the most amount. So, important question then is what actually increases this future value? What increases the amount A you get at the end? Well, as you imagine, increasing the principal, what you start with, the more you start with, the more you get at the end, because the interest is based off the amount you have in a present time. If you increase the interest rate, you can also get more. Increasing the time, the longer it stays in it, the more money you'll generate. And also increase the number of compounding periods per year. So the more often you compound, the more you make, although it's kind of diminishing returns as you go higher and higher. But this continuous compounding is a limit. So the fastest compounding you can get, or the biggest benefits you can get from increasing compounding, is given by this continuous compounding formula. Now, let's take a look at some examples to work with this and kind of get a feel for how we calculate interest. Let's look over here to the right, and we'll do some examples. Okay, so this one is, we do 3 examples of different compounding periods and interest rates, slightly different interest rates, and we'll see how much we get. Okay, so here, as this says, we're going to start with an initial investment of $10,000 for 5 years. We'll find the future value. So right away, we see in each one of these cases, our P for each case, 1 through 3, is going to be 10,000. And then our T, time, is going to be 5 years. That's going to be the P here in our formula and the T in our formula. Now, let's take a look. The first case invested at an annual interest rate of 1.35% compounded quarterly. So it's compounded quarterly. So our M, our number of compounding periods per year, is then going to be quarterly, which is 4. And our interest rate, R, this we want to put as a decimal. We don't want to leave it like this. And also, we don't want to round off. So if you remember to convert a percentage to a decimal, move your decimal place 2 places to the left. So it'll be 0.0135. Don't round that off, leave it as it is. Now, if we plug all this in, what we'll have is that the amount is going to be 10,000 times 1 plus 0.0135 divided by 4. Then our exponent is 4, or which is our M times T, which is 5. Okay, now what I'm going to do is I'm actually going to use Desmos to calculate this. So I don't have a graphing calculator simulator to use at the moment. So we're going to use that to help us calculate these things. That'll be a good way to show how you should plug it in and what it looks like. And for a lot of your modern calculators, your TI like 8384s and others, you can actually put all this in at once, not have to calculate it in parts. That way you leave as much accuracy as possible for the calculator. So let's take a look at that. So remember, Desmos is just desmos.com. Click the graphing calculator. And all this is a graphing calculator. We can actually use it to calculate other things as well. So let's plug it in the way we saw it. So 10,000. Then in parentheses, I'm going to put 1 plus, then R was 0.0135 divided by, let's see, make sure we're not just dividing by that, 4. Okay. Then use the arrow, then close our parentheses, then put an exponent, and then it was 4 times 5, which was 20. And see, that tells us right there what we have. Okay. So what it tells us then is that for those conditions, at the end of 5 years, we'd have $10,697. And since this is money, round the nearest cent point and 9 cents. Let's go back. And so, as I said, that amount is going to be $10,697.09. That's the amount. Once again, starting with the same amount for $10,000 for 5 years. at 1.35% compounded quarterly. Now, let's take a look at our next example. So we're starting using the same P and same T. This time we're invested at an annual interest rate of 1.3% compounded monthly. This time our M is going to be monthly, which is 12. And our R is 1.3%, or let's convert this to a decimal, 0.013. Okay, and since we have a 0 there, we can leave that 0 off. All right, now what we expect is we're compounding monthly. That should increase our amount, but our interest rate is slightly less. Instead of 1.35%, it's 1.3. So the question is, do we get more this way or less this way? Let's find out. So once again, if we plug everything in, 10,000, then 1 plus 0.013 divided by 12. And then in our exponent, our compounding period is 12 times 5, our years, which that'll be 60. So once again, let's use Desmos to help us out. I'm actually going to start this over again so you can actually see each one here. So 10,000 times 1 plus, and then 0.013 divided by 12, and use the arrow. So let's close the parenthesis. And then in the exponent, that was 12 times 5, which is 60. And that, as you see, actually turns out to be a little bit less. So $10,671.21. In that case, even though we compounded more often per year, because our interest rate was slightly less, actually we got less money overall. So that amount, as you see, was equal to $10,671.21. So about what was that, about $26 less, approximately. And then one more example like that. So we're going to reduce our interest rate again, but we're going to compound daily. So we might expect once again it will be reduced, but let's find out. So here, daily compounding. Let's look back over here. Daily, we're calling 365 times a year. Our interest rate is 1.25%, or as a decimal, 0.0125. Once again, don't round that off. We plug this in. 10,000 times 1 plus 0.0125 divided by 365. And then here in our exponent, 365 times 5. Now here, I don't know what 365 times 5 is, but we'll plug it in just as it is, and that will show us. Once again, let's go back to Desmos. And same thing. So starting with the same principle, 10,000, then times 1 plus 0.0125, or 1.25% as a decimal, divided by 365. All right. We'll close the parentheses. Then as an exponent, this time we use parentheses as well. And 365 times 5. And this time, yeah, as we can see, it's actually less again. So $10,644.93. So I actually got less. So you see, it's kind of more, appears it's kind of more sensitive to your interest rate. The formula is kind of more sensitive to what your interest rate is and actually your compounding period. So once again, this amount was $10,644.93. Now, let's make a few things clear. If you left your interest rate the same in each of these three cases, then the more often you compound, the more money you would have. Or if you left your compounding period the same and reduced the interest rate, as we did, then you would have less. In this case, though, looks like it's more sensitive to the interest rate, and we got less by, although any benefits we got from compounding more often, we lost by reducing our interest rate. That's how the basic formula works. Let's take a look at a couple more examples. Now, this is a slightly different problem. It says if you want to have a total of $50,000 in 17 years after compounding daily at an annual interest rate of 5.5%, how much should you invest now? So if you notice, that's not exactly the same question we had before. Let's think about that. That's what it's asking for. So think about what our values are. So we have our A, let's look at these over here. So we kind of write down our unknowns, or A, P, R, M, and T. We need all these, or at least 4 of them, and to be able to find the 5th one. Okay, so some of these are clear. 17 years, that's our T, 17. Compounding daily, we just saw compounding daily, that's 365. Our interest rate is 5.5%, so as a decimal, it's going to be 0.055. So the question is this 50,000, is this the future value or the present value, or the initial interest rate? So it says we want to have 50,000 in 17 years. That's going to be our future value. So that's going to be 50,000. Now then the question is, what is P? So if you notice, this is different. In the other examples, we knew what P was, we found A, but here we're going the other way. Let's take a quick look at our formula. And a couple ways you can do this, but actually probably the easiest thing to do is take a look at this as a formula. Now, we want to find P, we want to get P by itself. So actually, remember this whole thing, this whole parenthesis for the exponent will be just a number. So we can actually divide both sides of this by that to get P by itself. If we do that, then we'll have P is equal to A, then divided by this whole thing. 1 plus R over M to the MT. Okay, and that gives us a formula then for finding our principal value, or our present value, our initial investment. That's the question, what should I invest now? That is the principal. So let's plug in everything we have. So we have $50,000. And then down here we have 1 plus R, which is 0.055. Once again, don't round that off. Our compounding period is 365 compounding periods per year. Then times 365 M times T, which is 17. Now, once again, we'll use Desmos to help us out with this. And that will kind of also show you what it'd be like to use like a regular modern calculator. Well, first off, let me write this down for myself to make sure I get everything right. Now, let's go back to Desmos. Now, I'll just leave all these up here. So we're going to have $50,000 divided by, use parentheses again, 1 plus interest rate 0.055 divided by 365. So once again, this looks just like what I was showing you there. Close the parentheses. Use an exponent, which is just the exponent in the denominator. And that's going to be, I use parentheses here as well, 365 times 17. Okay. Now, if you notice, it looks just like we showed it there. And so what that tells us then is the amount we're going to need to start up with right now under those conditions is $19,630.68, rounded to the nearest cent. So approximately 20% of that's approximately 20% of the $50,000 we're going to need to start with, once again, for that interest rate and for those conditions and for that time period. Let's go back, and that's the value we're going to need to start with to get $50,000 in 17 years. So that's, once again, $19,630.68. Okay, let's look at one more example. This one is, once again, a bit different again, what we're asking for. Beginning with $17,000, how many years will it take for the initial investment to grow to $41,000 at 2.95% annual interest, compounding continuously? Now, this says compounding continuously. So if you notice this time, the form we're going to be using is our continuous compounding formula. We use a different formula. Use A is equal to P e to the RT. So like before, let's write down our different parts here. A, P, R, T, and of course, remember E is approximately 2.718. Let's see what we have. So our interest, a couple things we know. Our interest rate is 2.95%, so as a decimal, it's 0.0295. And once again, don't round that off. We're compounding continuously. This time there's no M because that's actually taken care of in the exponential. So what else do we have? Well, says beginning with $17,000. If we're beginning with that, then as you expect, that's going to be our principal. That's 17,000. And then wanted to grow to this. So wanted to grow to something, that's going to be our A, our final, our future value. That's going to be 41,000. And then our T is what's unknown. The question is, how long will that take? Now, what we also want to do in this one is not simply just plug everything in, because that won't really work. What we do then is let's come over here. Let's actually solve the formula for T. Okay. So with an understanding of logarithms, we can do that. So use whichever log you want. I'll just use, let's use natural log, though it doesn't matter. I'm trying to think if I want to, a couple ways I can approach this, but yeah, let's use natural log. Okay. Where ln is natural log, and that's the inverse of E. So let's take the natural log of both sides. And so what I do is then ln A is equal to ln times this whole side, P e to the RT. Okay, now, what does that do for us? Well, over here, I can use properties of logarithms to simplify this and expand it out. So the left side is still the same. So since this is a product, I'm multiplying P times the exponential. Then I can essentially add these. It's going to be natural log of P plus the natural log of E to the RT. Okay, now use another, and here, what happens here is natural log and E are inverses of each other. So actually those cancel out. What I'm left with then is the natural log of A is equal to the natural log of P is equal to R times T. Okay, oops, sorry, that's a plus, not a equal there. Okay, now I want to solve this for T, get T by itself. So remember, these are all just numbers. So subtract natural log of P from both sides. So I have natural log of A minus the natural log of P is equal to R times T. And then finally divide both sides by R. And so I'm going to get T is equal to natural log of A minus the natural log of P divided by R. That gives me expression for the time for continuous compounding. Now let's plug in my values. When I plug in my values, I have T is equal to the natural log of A, and A was $41,000. So natural log of 41,000 minus natural log of P, so natural log of 17,000. And then over R, and R is 0.0295. Once again, we'll use Desmos to help us out with this. So let me write it down so make sure I have everything. Okay, let's go back to Desmos and plug that in. Once again, in most calculators, you can do this. Now here, I'm going to move down a bit. Here, I'm also going to use parentheses here because I want to divide the whole numerator. So you ln of 50,000. You notice natural log of 50,000 is not a big number because the natural log is a very slow growing function. Then minus the natural log of 17,000. Okay, close the parentheses. Then divided by R, which is 0.0295, our interest rate is a decimal. It says that's going to be, let's round off to two decimal places, 57 years. So a little over, 36 years and about another 6 months approximately. So 36.57 years. So that's once again for those conditions. Continuous compounding, which remember is the fastest compounding. So we can't use any other compounding period to get faster for those same conditions. So for that amount, that interest rate, and you want to get this amount, that tells you exactly, it tells you how long it will take to get that. Once again, any other, using that same interest rate and the same amounts, any other compounding would be slower. So Of course, if you want to get there faster, then as we said, if you want to get there to $41,000 faster, you either have to increase your interest rate or increase your initial investment. So what we've seen so far is learned a bit about compound interest, learn what the formula is, how to use it, what the different compounding periods are, and they're able to find both a future value, which is A, find a present value needed to get to some future value, which is P, then also use continuous compounding, which is the limit, the fastest type of compounding you can do. And then from that, being able to find a time needed to get to a future value given a certain principle. Thank you. Have a good day.